You stand before the Pantheon in Rome. 2,000 years have passed. The walls have not moved an inch. You reach out and press your palm flat against the ancient stone. It feels impossibly solid, almost alive beneath your fingers. You know that modern buildings around you need repairs every few decades. This one has needed almost none in 2 millennia. Outside the city, Roman harbor walls still push back the relentless Mediterranean Sea, wave after crushing wave, century after century. You try to imagine what force of nature, what secret knowledge, allowed these ancient builders to create something so permanent. The stone beneath your hand is not natural rock. It was made by human hands, mixed from ash and seawater and lime. Somewhere deep inside this wall, a slow chemical reaction has been happening since the day it was cast and left to cure. That reaction does not weaken the structure. It does the opposite. It makes the wall stronger every single year that passes. You are not touching concrete as we know it. You are touching something closer to living, growing mineral rock. Every storm, every tide, every earthquake tremor has only fed the process, deepening the crystal lattice hidden within the walls. Roman engineers had no laboratories or electron microscopes. They had observation, tradition, and access to the most powerful volcanic ash on Earth. That ash, carried from the slopes of ancient volcanoes, became the secret ingredient in history's most durable building material. You look up at the Pantheon's vast, unreinforced concrete dome. No steel bars inside, no modern scaffolding ever held it up. It has carried its own weight in silence for 1,900 years, and today it shows no sign of surrender. This is the story of Roman concrete, the secret to eternal strength that humanity lost and is only now rediscovering. Roman concrete is known by its Latin name, Opus Cementicum. It emerged as a dominant building material around the 3rd century BCE. Researchers at Sapienza University of Rome found that early Romans observed volcanic soils bonding with remarkable tenacity when wet. The key discovery was pozzolana, a fine volcanic ash harvested near the ancient town of Pozzuoli on the Bay of Naples. Pozzuoli sat atop the Campi Flegrei volcanic field, one of the most geochemically active regions in the entire Mediterranean world. The ash from that landscape carried unique silica and alumina compounds, becoming the chemical engine of Roman permanence. Marcus Vitruvius Pollio, great Roman engineer, described this material in meticulous detail in his celebrated treatise, De Architectura. Vitruvius noted that this volcanic powder, when mixed with lime and water, produced a mortar of extraordinary and lasting hardness. He specifically noted that seawater mixed with pozzolana produced concrete of exceptional, almost supernatural enduring strength for maritime structures. Scholars once viewed this as mere practical observation. Modern chemistry reveals it as one of history's most precise engineering insights. Researchers at UC Berkeley, led by Dr. Marie Jackson, began systematic analysis of Roman marine concrete samples in the 2000s. Using X-ray diffraction and electron microscopy, Jackson's team examined harbor concrete from Caesarea Maritima across the entire Mediterranean coast. Published in American Mineralogist in 2017, their findings revealed a mineral unknown in engineered concrete before, altobermarite crystals. These crystalline structures were not present when the concrete was poured. They grew inside as seawater permeated across the centuries. Pozzolanic chemistry is triggered when calcium and lime meet silica and alumina compounds locked deep inside the volcanic ash. Modern Portland cement reacts rapidly but incompletely, producing a rigid matrix that grows brittle and crack-prone within mere decades. Roman concrete reacts slowly over centuries, growing interlocking mineral crystals that seal any microfracture before structural failure occurs. The Oxford Research Encyclopedia confirms Roman builders understood aggregate selection as a critical variable in construction quality and longevity. Romans packed broken tuff, pumice, ceramic fragments, and rubble into the binding paste, creating a composite with distributed internal stress resistance. This aggregate choice was not random. Pumice and tuff are volcanic in origin, chemically compatible with the pozzolana binder surrounding them. The British Museum holds construction records showing Roman contractors specifying material sources with remarkable precision for each different building type. Harbor walls required sea sand and seawater in the mix. Interior vaults used lighter pumice to reduce the dome's dead load. The Pantheon's upper dome, analyzed by Politecnico di Milano engineers, contains progressively lighter aggregate toward the oculus to manage stress. This deliberate density gradient represents a structural optimization that modern engineers still describe as sophisticated by contemporary computational standards. The Roman state never left concrete quality to chance. Military engineers maintained rigorous oversight of all major imperial construction programs. The Cursus Honorum placed experienced military engineers in infrastructure authority, embedding technical expertise directly into Rome's governance structures. State-controlled lime kilns and standardized pozzolana quarries near Pozzuoli ensured consistent concrete quality across the entire empire's construction program. Cambridge University classicists documented that Roman harbor walls in Britain and Egypt were built from the same standardized chemical principles. Roman concrete was not a secret formula. It was a codified, institutionalized, empire-wide engineering standard maintained for over 5 centuries. When the Western Roman Empire fragmented in the 5th century CE, knowledge of pozzolana quarrying and opus cementitium fragmented with it. Medieval builders, lacking volcanic ash and institutional knowledge, reverted to mortared stone. The concrete tradition went dormant for 1,000 years. To understand why Roman concrete outlasts our own, think of Portland cement as a photograph and Roman concrete as a living organism. Portland cement hardens completely within days of pouring. Its crystalline structure is fixed, static, unable to respond to future stresses. When Portland concrete cracks, water enters, steel reinforcement corrodes, and the structure weakens through carbonation and chloride ingress over time. Roman concrete does the opposite. When seawater enters a microcrack, it deposits new crystalline material inside the fracture, healing it. Dr. Jackson's team confirmed altobermarite and phillipsite crystals nucleate at crack boundaries, stitching the damage closed at the molecular level. This self-healing mechanism is not metaphorical. Crystals physically interlock across fracture surfaces, restoring compressive strength beyond the original material's density. Think of Roman marine concrete as armor that absorbs every blow and grows harder precisely at the point of impact. The Portus Harbor complex near Rome, studied by the British School at Rome, shows breakwaters continuously reinforced by natural crystal growth. Caesarea Maritima's harbor deployed concrete forms submerged directly into the Mediterranean seabed more than 2,000 years ago under Roman supervision. Marine archaeologists diving the site describe that concrete as indistinguishable in hardness from the surrounding natural limestone bedrock beneath the sea. The Pantheon's dome spans 43.3 meters without a single steel reinforcement bar anywhere within its magnificent concrete body. The dome was cast in a single continuous pour over wooden formwork, which was removed once the concrete fully cured. At the summit, the 9-meter oculus eliminates central compressive load, allowing the dome's weight to distribute perfectly down-curved ribs. Structural analysis by the Politecnico di Milano confirms the Pantheon dome operates in nearly perfect compressive equilibrium, ideal for unreinforced concrete. The Roman formula used pozzolana from the Alban Hills mixed with lime and fresh aggregate, producing exceptional early-age compressive strength. The Baths of Caracalla, completed in 216 CE, deployed Roman concrete in vaulted halls covering over 11 magnificent hectares. Each vault required precise formwork geometry, carefully graded aggregate, and controlled curing managed by state-employed engineers and skilled freedmen laborers. The bath's concrete used lighter aggregate in upper vaults and denser mixes at the base, where compressive forces were greatest. Think of Roman engineers as the operating system of civilization, invisible code running beneath the marble surface, enabling everything beautiful above it. The Via Appia's foundation layers used hydraulic concrete that cured perfectly in damp soil conditions without any deterioration over centuries. If Roman roads were the empire's nervous system, Roman concrete was the myelin sheath keeping every signal moving cleanly through the network. Trajan's markets, built around 100 to 110 CE, used Roman concrete floor vaults, still bearing the weight of visitors every single day. That concrete has been continuously loaded for 19 centuries without structural failure. No modern office building approaches a comparable lifespan. Roman engineers developed formwork techniques using hollow ceramic tubes, tegulae, embedded within concrete vaults to reduce mass while maintaining structural geometry. These embedded tubes function like the cells of a bone, distributing stress through a 3-dimensional lattice rather than concentrating it at rigid contact points. Roman engineers in North Africa built concrete cisterns using pozzolana imported from Italy, proving the material justified long-distance shipping logistics. The Pont de Garde aqueduct in southern France uses Roman hydraulic concrete in its channel lining, still functional after 2 millennia. Engineers at MIT proposed Roman concrete microstructure could yield a low-carbon cement alternative, as pozzolanic reaction requires far lower kiln temperatures. Portland cement contributes approximately 8% of global CO2 emissions. A Roman-inspired pozzolanic cement could reduce that figure by 40%. Roman engineering intelligence was not primitive. It was simply operating on a different timescale, measured in centuries rather than fiscal quarters. You now know what hides inside those ancient walls, not just stone and ash, but a philosophy of building encoded in molecular chemistry. The Romans did not build for the next election cycle. They built for the generations they would never meet and never know. You live today in a world shaped by structures engineered to outlast every empire, every war, and every forgetting of their makers' names. The Pantheon does not know your name, but it has sheltered 2,000 years of human prayers, art, and grief within its walls. A Stoic principle lives at the heart of Roman concrete. Strength is not resistance to change, but transformation through pressure into something more enduring. Virtus, the Roman ideal of moral excellence, was not merely personal virtue. It was embedded in the materials they used to build their world. You carry that same potential. Every discipline you maintain, every foundation you lay in patience, becomes a crystal structure no storm can shatter. Researchers now synthesize Roman-inspired concrete using volcanic ash from Mount Shasta, Sicily, and Iceland, recovering what millennia of forgetting erased. In 2023, a Princeton University team successfully replicated self-healing Phillipsite crystallization in laboratory pozzolanic concrete, a quiet revolution. The ancient world is not behind us. It is beneath us, holding us up, waiting for us to remember what it knew. Every time you walk across a modern bridge, you benefit from a conversation that began in the volcanic fields of Campania. Roman engineers did not fear impermanence. They mastered the chemistry of permanence and poured it into the ground for those who would follow. The deepest lesson of Roman concrete: greatness is not loud or fast. It is patient, molecular, and invisible until centuries reveal it. You now see what astonished you at the Pantheon not as mystery, but as mastery, knowledge, intention, and extraordinary respect for the future. 2,000 years from now, something you build with patience and integrity may still be standing. The Romans proved it possible. The question is yours.